Howdy, students. Hope all is well. Um, didn't necessarily want to fully finish a few problems, but I wanted to at least set up a few problems. The first one is number 64 on page 1035 in the book. So this is the double integral over the region of the function x minus y, x squared plus y squared plus 1 dA. And it tells us that the region R is the region inside of the unit circle centered at the origin. Okay, so in order to set this up, notice that the x squared plus y squared part tells me that I pretty much want to use the fact that I can do this in polar coordinates. So x equals r cosine theta, y equals r sine theta, and then of course through the Pythagorean theorem, blah blah blah, we know that x squared plus y squared is just going to equal r squared. Check. Okay, so making these substitutions, our integral becomes the integral of r, and then I'm going to write this a little teeny bit funny, but this is going to be r times, so then x is cosine theta minus sine theta over, and then again here I'm going to write this slightly funny just because I don't need to put the whole thing over the bottom. I can just divide the front part, and then this just becomes r squared plus 1. And then because we're doing this in polar coordinates, our dA, remember dA needs to be r dr d theta. So this is going to be r, which I'm going to move all the way over and multiply times that, dr d theta. Okay, now before I actually evaluate this, I should note I'm going the unit circle r, so I'm going from 0 to 1 in r, and I'm going all the way around the unit circle, so that is from 0 to 2 pi in theta. Okay, so as far as this r integral though goes, this theta part of it is just a constant. So let's pull that out just like we would pull a constant out in front of the integral. And if we notice, and then we could write this as the integral from 0 to 2 pi cosine theta minus sine theta times, and then big parentheses, the integral from 0 to 1 r squared over r squared plus 1 dr d theta. Okay, so I don't need to evaluate that because I know if I integrate cosine from 0 to 2 pi, well, at 0, I'm going to get a sine out of this, and at 0 I get 0, and at 2 pi I also get 0. So I get 0 minus the sine is going to give me a cosine. 1 minus 1, that's again 0. So this part of it, when I evaluate it, is just going to give me 0. So I don't need to do this. I know the answer is just 0. We should actually see that that comes in because the original function, this is just depending on r, But this part, if I were to reflect over the line x equals y, so I switch my x and y, then it just makes it negative. So any value here is the negative of the value there. So of course, if I integrate over all of those, I have to get 0. Okay, hope that makes sense for that one. Let's look at a couple more real fast. Next one I got is, let's see, this one's number 54 on page 1025. Okay. Double integral over the region of y over 1 plus x plus y squared dA. And then here it gives us a weird one. It says the region equals the set of x and y such that 0 is less than or equal to the square root of x is less than or equal to y is, and 0 less than or equal to y less than or equal to 1. Okay. So if we were to just kind of want to set it up based on these, then my x depends on my y, and I could set this up as the integral of y over 1 plus x plus y squared. And then if I do this with respect to x first, then I can just rewrite this. So 0 less than or equal to the square root of x less than or equal to y is the same thing as just squaring each of these things. And then I can say my x goes from 0 to y squared, and my y goes from 0 to 1 dy. Okay. And now, if I were to evaluate this, with respect to the x, I really have a constant time plus x. And then this y is just a constant on top that I can pull through the first integral. Okay, so we've really got like a 1 over a plus x that we're integrating. So that's just going to be an ln of a plus x. So that would give us integral 0 to 1 of, now I have y times the natural log of 1 plus x plus y squared, and I need to evaluate that at 0 and y squared dy. And we can see that that's now going to give me the integral from 0 to 1 of y ln of 1 plus 2 y squared minus y ln 1 plus y squared dy. So these are integrals that one could do, but that's kind of a pain. So let's see, actually. So that region, if I were to graph it, graphing this equation, I think is actually almost easier to graph as that equation. So this is y squared and my x values, so x gets bigger if I go to the right and smaller to the left, and my x values need to be less than that, but greater than 0. Check, and my y values can be from 0 up to, we'll say, there's 1, and I have this region here. Oh, well, just converting this function, if this is y squared, then that's the function square root of x, and my x values need to range, my y values need to range from the square root of x up to 1. And my x values can go from 0 to this point where these two intersect, which is where the square root of x equals 1, which is just 1. So x is greater than or equal to 0, less than or equal to 1. Okay, so we could set it up that way. Let's try that real quick. Jumping in here, this gives me the integral y over 1 plus x plus y squared, which now I'm going to integrate it dy dx. So my y limits come first, and this is the square root of x to 1 and 0 to 1. Okay, so now doing this, I can actually see I've got kind of a u substitution here because I've got a y squared and a y. So I'm going to say u equals 1 plus x plus y squared, and then my du will equal 2y. And when we end up doing this, we get the integral from 0 to 1 of the natural log 1/2 the natural log of 1 plus x plus y squared evaluated at the